Welcome back, everyone, to Neural Intel.
Great to be here.
Today, we're really diving into something quite specific and technical in medical imaging.
Yes, it's about automatically finding, well, segmenting lung tumors in CT scans, reliably doing that.
And we're basing this on a paper one of our listeners pointed us to, right?
That's right. It's called Uncertainty-Guided Coarse-to-Fine Tumor Segmentation with Anatomy-Aware Post-Processing. Quite a mouthful.
Yeah. It's from the ACDSA conference 2025. So our mission today is really to unpack the tech behind this.
Exactly. How does this system work? What problems is it trying to solve? And what are the potential, implications for accuracy and reliability? We'll stick to the technical side.
Okay, let's start with the challenge itself. The paper makes it clear this isn't easy. Why is segmenting lung tumors so technically difficult?
Well, there are quite a few hurdles. For one, the tumors themselves can look very different internally. That's tumor heterogeneity.
Okay, so they're not just uniform blobs.
Not at all. Then there's the sheer scale difference. You have vast amounts of healthy lung tissue and maybe only small tumor regions. That's class imbalance.
Makes it hard for an AI to find the target.
Definitely. And then, down at the voxel level, the tiny 3D pixels in the scan, you might get a mix of tissues in one voxel. Partial volume effects. It blurs things.
Right, that just fuzzy.
Exactly. And that boundary ambiguity is a major issue, especially near tricky areas like the pleura, the chest wall lining.
Or the mediastinum, that central chest area.
Precisely. Or the central airways, the hilar regions. Tumors there can be hard to define. They might even grow across these lines.
And the paper mentions some tumors aren't even fully inside the lung tissue.
Yeah, that's a key clinical point they address technically. While most are within the lung parenchyma, some important ones actually push beyond the lung walls. The system needs to handle that too.
So it's clear that just getting a high accuracy score, like a good DICE score, isn't the whole story for clinical use.
Not at all. The researchers really emphasize this. You need spatial reliability, knowing where the prediction is accurate. You need fewer false positives, fewer incorrect flags.
And crucially, understanding where the system isn't sure. That uncertainty piece.
Exactly. That's vital for a clinician reviewing the results.
Okay, so given all those challenges, what's their proposed solution? They talk about a two-stage coarse-to-fine framework.
Yeah, that's the core idea. Break it down into two steps.
What's the first stage?
Stage one is coarse localization. They use a 3D deep learning model, something like a UNet or UNetter, to look at the entire CT scan volume.
The whole thing at once.
Yes, to get a first rough idea where potential tumors might be. It's like a quick, broad searchlight. Importantly, they don't model uncertainty at this stage.
Okay, just finding candidate zones, then what?
Then they apply something called connected component analysis to that initial prediction map. It basically groups the predicted spots into distinct candidate regions, like potential individual tumors.
Got it. And those candidates move to stage two.
The most promising ones do, yes. Stage two is ROI-based refinement. ROI means region of interest.
So focusing in.
Exactly. A second model, trained for high-resolution work, takes these smaller candidate regions and does a much more detailed segmentation within just those areas.
And this stage incorporates uncertainty.
Yes. That's where the uncertainty modeling comes into play, trying to make the detailed segmentation more robust, especially at the edges.
But wait, there's a step between these two stages, right? This anatomy-aware post-processing. That sounds important.
Oh, absolutely crucial. Before the refinement stage, they apply this filtering step that uses anatomical knowledge.
How does that work? What does it do?
Several things. First, component merging. The coarse prediction might sometimes split a single tumor into, say, two nearby blogs.
Oh, okay.
So they use a kind of 3D smoothing kernel to connect fragments that are close together, trying to reconstruct the whole potential tumor.
Makes sense. What else?
Lung overlap filtering. They generate a mask, like a digital outline, of the patient's lungs. Then, for each candidate tumor region from stage one.
They check how much is actually inside the lung?
Right. If a candidate has very little overlap, the paper mentions generally below 80%, it's likely a false positive, maybe some noise or another structure, especially if it's in the central chest area.
Yeah.
So they often discard those.
But they're careful near the edges of the lungs.
Yes, the filtering is more lenient there because tumors can grow on the periphery.
So how do they handle those edge cases?
They add another check. Distance to lung surface. If a candidate has low lung overlap, BUT, it's very close to the lung boundary, say, within 5 voxels, and it's not tiny.
They keep it.
They keep it. It acknowledges that edge-growing tumors are a real possibility.
Smart. And there was one more filtering step. Something about top K.
Yeah, an optional step, top key component selection. After all the filtering, they can choose to keep only the largest candidate regions, ranked by volume. Maybe just the top one or top two.
And did that help? Just keeping the biggest ones.
Interestingly, yes. They found that keeping only the single largest candidate, top one, actually gave the best results in their experiments.
Really? Fewer candidates led to better final accuracy.
It seems so. They suggest it acts like a kind of spatial attention, really focusing the detailed second-stage model on the most probable area, reducing distractions.
Fascinating. Okay, let's go back to that second stage, the refinement. You said it uses uncertainty. How exactly do they model and use that?
They train that second-stage model using specific types of loss functions. These are uncertainty-aware loss functions.
What does that mean in practice?
It means that during training, the model is encouraged to pay more attention to the parts of the image where its prediction is uncertain. Usually that's the boundaries, the fuzzy edges of the tumor.
So it learns to focus on the tricky bits?
Kind of, yeah. It learns to recognize its own uncertainty.
And how is that uncertainty actually estimated?
They use a technique called Monte Carlo dropout, or MC dropout. Normally, dropout layers in a neural network are just used during training to prevent overfitting. But with MC dropout, they keep these layers active even during the prediction phase.
So when they're actually analyzing a new scan,
Yes, they run the prediction multiple times, and each time, different random neurons are temporarily dropped out. This gives slightly different results each time.
I see. And the variation between those results tells you how uncertain the model is.
Exactly. High variance means high uncertainty in that specific region of the image. It's like asking the model the same question multiple times and seeing how much its answer changes.
And this uncertainty information feeds back into the training.
Yes, that uncertainty-aware loss function uses this estimated variance. It adjusts the penalty for errors. An error in a high uncertainty region might be penalized differently, or perhaps more heavily, pushing the model to learn more about those ambiguous areas.
Okay, that's quite a sophisticated setup. So what happened when they tested this whole system? What were the key technical results?
Well, the main comparison was against a standard single-stage segmentation model, and their two-stage approach showed significant improvements.
Like with that dice score.
Yes, on their internal Orlando dataset, using a specific model architecture called Swin-U-Netter, the dice score jumped from 0.4690 to 0.6447.
That's a pretty substantial leap in overlap accuracy.
It really is. And they also saw improvements in spatial accuracy, measured by the Hausdorff distance. Lower Hausdorff means the predicted boundary is closer to the true boundary.
Which is arguably more important for things like treatment planning.
Absolutely. And remember that finding about keeping fewer candidates.
The top one selection giving the best results.
Yes, that was a strong finding. Reducing the number of regions passed to the second stage, especially down to just one, correlated strongly with better performance. They found a significant negative correlation between the number of components kept and the segmentation gains, especially for that Hausdorff distance measure.
So focusing the detailed model really paid off. Any other technical takeaways?
They looked at the lung masks used for filtering. Turns out, the quality of that mask didn't have a huge impact on the final outcome.
That's good news, right? Means standard automated lung segmentation is probably good enough.
Yeah, it suggests existing tools are sufficient for that part, making the whole pipeline more practical.
And the uncertainty-aware training. Did it always boost the raw scores like dice?
Not always,
Yeah.
interestingly. Compared to standard loss functions, it didn't consistently give higher overall dice scores in all configurations.
Oh, so what was the benefit then?
The benefit was more about the quality of the segmentation boundaries. It improved what they call spatial calibration, making the uncertainty estimates more reliable, especially at the edges. It makes the output more interpretable for a clinician. They can better see where the model is less confident.
That makes sense. Confidence maps are useful. Did they try different AI model types?
They did. They tested standard UNet, UNetter, and Swin-U-Netter within their framework. And they used both a private dataset and a public one, NSCLC radiomics. The Swin-U-Netter architecture seemed to benefit the most from their two-stage approach, particularly on their Orlando dataset, showing those big gains we mentioned.
Okay, so let's try and bring this all together. It sounds like a really well-thought-out, multi-step technical approach to a genuinely hard problem.
I think so. That combination of a broad initial look, then smart anatomy-based filtering, and finally a detailed refinement stage that's aware of its own uncertainty. It seems like a powerful strategy.
Yeah, and that finding about focusing on fewer high-probability regions, improving accuracy, that's technically quite insightful. It highlights how important intelligent pre-processing or, well, filtering can be.
Definitely. It's not just about throwing more compute power at the final step. It's about guiding that computation effectively.
And while the results look promising, it's obviously an ongoing area of research. Getting these systems truly ready for reliable clinical use requires continuous refinement.
Absolutely. But the papers focus on not just high scores, but also spatial reliability and that uncertainty component that really speaks to what's needed in a medical context.
For our listeners, I think this deep dive really illustrates how complex, real-world challenges in medical AI are being tackled. We've gone through the technical details, the model architectures, the training strategies like uncertainty-aware loss, the crucial post-processing steps.
It really shows that iterative process in research. You find limitations in one approach, and that drives the design of something more sophisticated, like this coarse-to-fine idea with anatomical smarts built in.
It certainly raises interesting questions about the role of uncertainty estimation in medical AI generally, and perhaps this two-stage approach could inspire solutions in other fields facing similar, noisy, complex data problems.
It's definitely a technique worth considering when you have that kind of scale difference or ambiguity.
If you want to get into the absolute nitty-gritty, the paper itself is on R6 identifier 2504.12215V1. Definitely worth a read for the full methodology. And please do keep checking our webpage link in the show notes to stay updated on the latest AI and ML research we're looking at.
Keep exploring, keep questioning.
And we'll catch you next time for another deep dive into the world of neural intelligence.